Greetings to everyone. So today we are going to discuss about two things. One is related to shape factor. Okay. So yesterday we have discussed that shape factor for three shapes. Okay. So one is for rectangular section. That is 1.5, and second one is for diamond section. That is 2. Then another one is triangular section, around 2.34 I came. Okay. Now today's class we are going to discuss about the circular section. Okay. Shape factor for circular section. So consider the circular section having the diameter of capital D. Okay. So that the neutral axis will be lies at the center of circular section. So that the centroid will be placed at y1 bar distance from above the neutral axis. Similarly, y2 bar is placed below the neutral axis, okay, at a distance of y2 bar. So CG1 and CG2. Now let us move on to the solution part. Okay. So here first shape factor S is equal to plastic section modulus divided by elastic section modulus. Here, whereas plastic section modulus ZP is equal to A divided by 2 into Y1 bar plus Y2 bar is our formula. Similarly, Z is equal to I by Y value, Y max. Okay. So here, area is equal to pi by 4 into D square. Okay. Next to Y1 bar and Y2 bar value. Okay. So this is nothing but 4r divided by 3 pi. That is the centroid distance. Okay, y1 bar and y2 bar. So this is nothing but 4r divided by 3 pi. So this 4r divided by 3 pi, I'm going to take it as a 2 into 2r divided by 3 pi. So r is nothing but radius. Okay. So 2r is nothing but our diameter of the circular section. So the formula is going to be changed as 2 into d divided by 3 pi. Now the ZP becomes, okay, pi by 4 into d squared divided by 2 into 2d divided by 3 pi plus 2d divided by 3 pi. Okay. Now I am going to take it as a pi by 4 into 2 becomes 8 d squared into 1 divided by 3 pi. I am going to take it as a common term such that our value becomes 2d plus 2d. It becomes 4d. Okay. So pi get cancelled. So our formula becomes 2, 4. Okay. So d cube divided by 6 is the value of ZP. Okay. Next Z value. So Z is equal to I by Y max. Okay. So here Y max is equal to D divided by 2. Okay. Whereas I is equal to pi by 64 into D power 4. So this is the formula for our I value. So therefore Z becomes, so pi by 64 into d power 4 divided by d by 2. So it becomes 32 and it becomes d cube So Z value becomes pi d cube divided by 32. Okay, therefore S becomes shape factor, S becomes, okay, Zp by Z. So Zp value is d cube by 6. Similarly, Z value becomes pi d cube by 32, such that d cube get cancelled. So 1 by 6 into 32 by pi. So the answer becomes 32 divided by 3 pi. Becomes, sorry, 32 divided by 6 pi. So it becomes 1.697. 1.697, the value for circular cross section. So if it is circular cross section, then the shape factor value for the section is 1.697. Okay. So next we should move on to I section. So for I section, we will go by a problem. Okay. So the given data, a mild I steel section, 200 wide and deep, has a mean flange thick. Sorry, 200 wide and 250 deep, has a mean flange thickness of 20 and a web thickness of 20 sorry, with thickness of 10 with thickness of 10 calculate the shape factor. Calculate the shape factor. Find the fully plastic moment. Find the fully plastic moment if yield stress is equal to 252 Newton per mm square. Okay, so the given data. So the given data are I section. Okay, so we have to draw the section details. Okay. We will draw in the next page. I section, that is, then sigma y they have given the 252 Newton per mm square. Okay. So I section of 200 wide, 250 deep, and flange thickness of 20 and web thickness of 10 Okay, so 200 wide, 250 depth. 20 mm thickness of flange. So thickness of flange becomes 20 mm. Web thickness 10 mm. So this is the given data. For this section, we need to find out the shape factor as well as fully plastic moment. So fully plastic moment MP is equal to sigma y into ZP. Okay. Similarly, shape factor S is equal to ZP by Z. Okay. Whereas Z is equal to, okay, uh, elastic section. Okay. We know the formula, that is I by Y. Okay. So I is equal to, for the entire section, capital B D cube, sorry, capital B D cube divided by 12 minus small b d cube by 12. So how the way I am going to calculate now? I'm going to do like this. So this one I am going to consider as capital B and this is capital D. And now this thickness from here to here I'm going to consider as, okay, small b, and from here to here I am going to consider as small d. Okay. So small b becomes 200 minus 10 divided by 2. Okay, no need. Actually, this is b by 2 and similarly this is b by 2. We can take like this. So total small b becomes 190 mm. And similarly small d becomes 210 mm. Okay. Now, so capital B is equal to 200 into 250 cube divided by 12 minus 190 into 210 cube divided by 12. So it becomes 200 into 250 cube divided by 12 minus 190 into 210 cube divided by 12. So the answer is 113.784. 113.784 into 10 to the power 6 mm power 4. This is the value of I for the entire section. And Y for the entire section is the total depth divided by 2. So Y is equal to 250 divided by 2. So 125 mm. Therefore, Z becomes 113 divided by this 125. So it becomes 910.273 into 10 cube mm cube. So this is the value of Z. Okay. Next, ZP. So ZP is nothing but A by 2 into Y1 bar plus Y2 bar. Okay. So area. So individual rectangular I am going to take. So 200 into 20, two plates are there. So 2 plus 210 into 10. So 200 into 20 into 2 plus 210 into 10. It becomes 10,100. 10,100 mm square. This is the value of area. Next to Y1 bar and Y2 bar. So section is symmetrical with respect to its neutral axis. Okay. So the neutral axis is going to lie at the midpoint of the section. That is Y value. It is 125 mm. Okay. So this is 200 mm. and this is 20 mm. This is 210 divided by 2, 105 mm, and the thickness is 10 mm. Now I have to find out the y1 bar distance. y1 bar and y2 bar are similar. Okay, so we should think about the section details. So y1 bar is equal to y2 bar is equal to a1 y1 plus a2 y2 divided by a1 plus a2. So a1 is nothing but this one I am going to consider as section 1. This is section 1 and this is section 2. Okay, so a1 is equal to 200 into 20, so it becomes 4000 mm square. Similarly, a2 is equal to 105 into 10, so it becomes 1050 mm square. So next, y1 bar, sorry, y1. So from the neutral axis to this position depth is y1, and for this position is y2. Okay, so y1 is equal to 105 plus 20 divided by 2, so it becomes 115 mm. Similarly, y2 is equal to 105 divided by 2 for the rectangular section. Okay, so 105 divided by 2 becomes 52.5 mm. Therefore, y1 bar is equal to y2 bar is equal to, substitute those values. So 4000 into 115 plus 1050 into 52.5 divided by 4000 plus 1050. So if I'm going to substitute these values, I can get the answer for y1 bar and y2 bar. So 102 mm is the value of y1 bar and y2 bar is equal to 102 mm. Therefore, ZP becomes area by 2, 10,100 divided by 2 into 102 plus 102. So 10,100 divided by 2 into 102 plus 102. It becomes 1.03 into 10 to the power 6 mm cube. This is the value of ZP. Now the shape factor S is equal to ZP by Z. So 1.03 into 10 to the power 6 divided by Z value 910.273. 910.273 into 10 to the power 3. So it becomes 1.0306 divided by 910. 910.273. So the value of shape factor becomes 1.132 S value. So that's why Yesterday we have said approximately 1.15 for I section. Okay, when we are seeing the discussing the introduction part. Okay. Next, they have asked to fully plastic moment. Therefore, fully plastic moment is equal to MP is equal to sigma y into ZP. So sigma y value they have given us 252. ZP value 1.03 into 10 to the power 6. So 1.03 into 10 to the power 6 into 252. So the total moment value is 259.56 into 10 to the power 6 Newton mm, or else MP is equal to 259.56 kilonewton meter. So this is the answer for our question. Next we should move on to the topic of what is plastic hinge and what is plastic hinge and what is plastic mechanism, that we are going to discuss now. Okay, now then after we will move for plastic analysis. Okay, so now what is plastic hinge? What is plastic hinge, that we are going to discuss now. So as we are discussing that, we are denoting the hinge like this, that is at the end of the support. So for example, if I am having the support like this, okay, so I am going to mention the hinges like this. Okay, so what is plastic hinge, how it is going to create, that we are going to. So first of all, fully plastic moment, that we have discussed, that sigma y into ZP, okay, is considered to have developed at any section of a structure, subjected to a system of loads when the section is completely yielded or plastified. So this is nothing but, if we already seen that stress strain diagram, okay, now stress distribution diagram. So here, once I am going to apply the load, the neutral axis will be here. Okay, so with respect to the neutral axis, how the section is going to deform. Okay, so my neutral axis will be here. If sigma y is less than sigma y, then it will be in the elastic state. Okay, at equal to y also, it is in elastic state only. Okay, sigma is equal to sigma y, then also it is equal. Okay, now if it is more than sigma y, that time the extreme fiber got complete stress, that is it reaches the ultimate stress. Okay, now so again the load is increasing, no, that time what will happen, no, the extreme fiber is going to, that is the adjacent fiber is going to reaches its maximum stresses. Okay, so such that it is going to increase. Okay, now once the ultimate yield stress is going to reach as the ultimate stress, automatically it will become like a rectangular section in the both above and below the neutral axis part. So this is the system called fully plastic movement. At that time, the hinges we are called it as a plastic hinge. Okay, now that only they are going to say. So consider at any section of the structure subjected to a system of loads when the section is completely yielded or plastified. Okay, completely yielded or plastified means it reaches the maximum stress. Okay, now so that time, okay, the fibers. Okay, now so here the fibers are going to reach as the maximum stresses in the above the neutral axis. Similarly, below the neutral axis, the fibers have reached the maximum stresses. Okay, now so that time the section act like a the section act like a hinge, like a hinge. This hinge is known as This hinge is called as plastic hinge. Okay, so this hinge is called as a plastic hinge. So in other hand, we can define like this. That is, plastic hinge is defined as the plastic hinge is defined as the plastic hinge is defined as an yielded zone, an yielded zone due to bending in a structural member, bending in a structural member, comma, at which large rotations, large rotations can takes place, can takes place at a section at a constant plastic moment. So here it is MP, the rotation is called theta. Okay, so if the section is like this, okay, then I am going to give the hinges like this. If I'm going to have the load like this, then because of this load, I can get the rotation like this. Okay, so this rotation is called theta, and here the moment is going to happen. This is called plastic moment. Okay, this is only they have explained. If the support condition, the support is hinged, the support is simply supported or hinged support, simply supported or hinged. Okay, then the moment value mp at ends is equal to 0. Okay, we all know that the simply supported means the end moment become 0. Okay, if it is fixed support or continuous support, continuous support, you know, then we can have the value of mp. Okay, so this is we have to remember. Okay, so this is the related the things about plastic hinge. Okay, have you got it? So by using this we are going to do the problem. Okay, now for the plastic analysis for the continuous beams. Okay, as per our syllabus.